Throughout human history, our curiosity about the stars and the cosmos has driven us to make incredible discoveries in astronomy. These findings have expanded our understanding of the universe, reshaped our view of reality, and sparked new questions about our place in the cosmos. From ancient civilizations to modern-day observatories, astronomical discoveries continue to amaze and inspire. In this episode, we'll dive deep into some of the greatest astronomical discoveries that have transformed our understanding of the universe, spanning from the early days of astronomy to the latest cutting-edge research. One of the most revolutionary discoveries in astronomy was the realization that the Earth is not the center of the universe. For centuries, ancient civilizations, including the Greeks, believed in the geocentric model of the universe, where the Earth sat at the center and all celestial bodies orbited around it. This model was supported by the great philosopher Aristotle and refined by Ptolemy, whose system of epicycles explained the complex motion of planets. However, in the 16th century, Nicholas Copernicus proposed a daring alternative, the heliocentric model. According to Copernicus, the Earth and other planets orbit the Sun, which lies at the center of the solar system. This idea challenged centuries of established thought, but ultimately led to a major shift in how humanity viewed its place in the cosmos. Building on Copernicus' ideas, Johannes Kepler refined this model by describing the orbits of planets as elliptical rather than circular. Meanwhile, Galileo Galilei provided observational evidence through his telescope that supported heliocentrism. Galileo's observations of Jupiter's moons and the phases of Venus were critical in confirming the validity of the heliocentric theory. This shift to heliocentrism not only revolutionized astronomy, but also set the stage for a scientific revolution, changing our understanding of physics, mathematics, and the universe's structure. With the heliocentric model laying the foundation, the next leap in understanding came from Johannes Kepler. Building on the accurate astronomical data collected by his mentor, Tycho Brahe, Kepler worked out three laws that describe the motion of planets around the Sun. These laws provided the mathematical framework that explained the mechanics of the solar system, and they remain essential to understanding orbits today. First law: planets orbit the Sun in elliptical paths, with the Sun at one focus of the ellipse. Second law: a line drawn from a planet to the Sun sweeps out equal areas in equal times. This means planets move faster when they are closer to the Sun and slower when they are farther away. Third law: the square of a planet's orbital period is proportional to the cube of the semi-major axis of its orbit. This law links the time it takes for a planet to complete an orbit to the size of its orbit. Kepler's laws were essential in forming a clearer picture of planetary motion, but there was still one fundamental question left unanswered. Why do planets follow these elliptical orbits? To answer that, we turn to Isaac Newton. Isaac Newton's law of universal gravitation provided the missing piece of the puzzle, the force that governs the motion of planets and all objects in the universe. Before Newton, there was no clear understanding of why planets followed the elliptical orbits described by Kepler. Newton solved this puzzle with his law of gravity, which stated that every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. Newton's work not only explained the motion of the planets, but also applied to all objects, from apples falling to the ground to the motions of galaxies. His law of universal gravitation became one of the cornerstones of classical mechanics and allowed scientists to calculate the forces acting on celestial bodies and predict their motion with great accuracy. Newton's contributions gave us the ability to model the universe with remarkable precision. But just as we thought we had a firm grasp of the cosmos, a monumental discovery in the 20th century would once again change our understanding: the revelation that the universe itself is expanding. In the early 20th century, astronomers believed the universe was static and unchanging. However, this view was challenged by one of the most profound discoveries in modern astronomy: the expansion of the universe. In the 1920s, American astronomer Edwin Hubble made an astonishing observation. Using the powerful 100-inch Hooker telescope at the Mount Wilson Observatory, Hubble observed distant galaxies and noticed that they appeared to be moving away from us. More importantly, the farther a galaxy was, the faster it seemed to be receding. This phenomenon, known as redshift, indicated that the universe was expanding. Hubble's discovery revolutionized our understanding of the cosmos, providing the first strong evidence that the universe had a beginning, a point in time when it was much smaller and denser. This led to the development of the Big Bang theory, which describes the birth and evolution of the universe. The discovery of the expanding universe was just the beginning. In the 1960s, scientists would uncover another groundbreaking piece of evidence that would solidify the Big Bang theory as the leading explanation for the origins of the universe. One of the strongest pieces of evidence supporting the Big Bang theory came in 1965 when American radio astronomers Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background (CMB) radiation. While working on a sensitive microwave antenna, they detected a faint, uniform signal coming from all directions in the sky. Initially, they thought it was interference from bird droppings or equipment malfunction, but eventually, they realized they had stumbled upon the relic radiation from the early universe. The CMB is the afterglow of the Big Bang, radiation left over from when the universe was just 380,000 years old. At that time, the universe had cooled enough for light to travel freely, and the CMB is a snapshot of that moment. The discovery of the CMB provided compelling evidence for the Big Bang theory and allowed scientists to study the conditions of the early universe in unprecedented detail. With the CMB confirming the Big Bang, astronomers turned their attention to exploring the wider universe. This led to one of the most exciting discoveries of the late 20th century, the existence of planets beyond our solar system. For centuries, humans have wondered whether other planets exist beyond our solar system. This question was finally answered in 1992 when astronomers Alexander Wolszin and Dale Frail discovered the first exoplanets orbiting a pulsar, a highly magnetized, rotating neutron star. The discovery of these planets, named PSR B1257 plus 12b and C, was a breakthrough in the search for other worlds. The real flood of exoplanet discoveries came later, especially with the launch of the Kepler Space Telescope in 2009. Kepler's mission was to search for Earth-like planets orbiting other stars, and it did so with remarkable success. As of today, thousands of exoplanets have been confirmed, ranging from gas giants like Jupiter to rocky, potentially habitable planets like Earth. The discovery of exoplanets has opened a new frontier in astronomy, with scientists now exploring questions about the potential for life beyond our solar system. But while the search for exoplanets continues, astronomers have uncovered even more mysteries within our universe. Mysteries that involve invisible forces shaping the cosmos. As astronomers studied the motions of galaxies and galaxy clusters in the 20th century, they encountered a perplexing mystery. The visible matter in these objects did not account for the gravitational forces observed. Something else, something invisible, seemed to be providing additional mass and gravitational pull. This mysterious substance was dubbed dark matter, and it remains one of the greatest unsolved mysteries in astronomy today. Dark matter is thought to make up about 27% of the universe's mass, yet we cannot directly observe it because it does not emit or interact with electromagnetic radiation, light. Its presence is inferred from its gravitational effects on galaxies and galaxy clusters. In addition to dark matter, astronomers also discovered another cosmic enigma: dark energy. In the late 1990s, two independent teams of astronomers discovered that the expansion of the universe was accelerating, a phenomenon that was unexpected and difficult to explain. Dark energy, which is thought to make up about 68% of the universe's energy content, is driving this acceleration, but its true nature remains elusive. These dark forces, which together make up 95% of the universe, are mysteries we have only just begun to explore. At the same time, a discovery first predicted by Einstein has opened a new window into the universe: the detection of gravitational waves. Black holes, regions of space-time where gravity is so strong that not even light can escape, have fascinated astronomers since their existence was predicted by Albert Einstein's theory of general relativity in 1915. However, it wasn't until 1971 that the first black hole, Cygnus X1, was confirmed through observations. The study of black holes has since become a major area of research, with scientists discovering supermassive black holes at the centers of galaxies, including our own Milky Way. In 2019, the world got its first ever image of a black hole, the supermassive black hole at the heart of the M87 galaxy, thanks to the Event Horizon Telescope. Another groundbreaking discovery related to black holes came in 2015 when the LIGO, Laser Interferometer Gravitational Wave Observatory, collaboration detected gravitational waves for the first time. Gravitational waves are ripples in space-time caused by the acceleration of massive objects, such as the merging of black holes. This discovery confirmed a major prediction of Einstein's theory of general relativity and opened a new way to observe the universe. With gravitational waves now offering a new perspective on cosmic events, astronomers are expanding their efforts to search for life beyond Earth, especially on nearby planets and moons. The search for extraterrestrial life has long been a driving force in astronomy. Mars, with its similarities to Earth, has been one of the prime targets in this search. Early observations suggested that Mars might have once had liquid water on its surface, and recent missions, including NASA's Curiosity and Perseverance rovers, have provided evidence that Mars had a habitable environment in the distant past. Beyond Mars, astronomers are exploring other worlds in the search for life. The icy moons of Jupiter and Saturn, such as Europa and Enceladus, have become promising candidates in the search for extraterrestrial life. Both moons are thought to harbor subsurface oceans beneath their icy crusts, and recent observations suggest that these oceans could have the necessary ingredients to support microbial life. In 2017, astronomers made a groundbreaking discovery in the field of astrobiology. They detected organic compounds, including complex molecules, in the geysers spewing from Enceladus. These organic compounds, along with the presence of water and energy sources from hydrothermal activity on the ocean floor, make Enceladus one of the most likely places to find life in our solar system. Beyond our solar system, the discovery of exoplanets, particularly those located in the so-called habitable zone of their stars, has added excitement to the search for life. While the search for extraterrestrial life is still in its early stages, the future of astronomy promises even more extraordinary discoveries. As we look to the future, the field of astronomy is poised for even more extraordinary discoveries. Advances in technology, such as the development of more powerful telescopes and the application of artificial intelligence, are enabling astronomers to peer deeper into the universe and analyze massive datasets with unprecedented precision. The upcoming launch of next-generation telescopes, like the Extremely Large Telescope, ELT, and the Square Kilometer Array, SK, promises to revolutionize our understanding of the cosmos. These instruments will allow us to study the first galaxies that formed after the Big Bang, investigate the nature of dark matter and dark energy, and perhaps even detect signs of life on distant exoplanets. The study of gravitational waves is another field that is set to expand rapidly in the coming years. With more sensitive detectors and collaborations around the globe, astronomers hope to observe events such as neutron star mergers, which could shed light on the formation of heavy elements like gold and platinum. Additionally, the detection of gravitational waves from more exotic phenomena, such as the collision of black holes with neutron stars, will help us understand the extreme physics of the universe. Furthermore, the search for life beyond Earth continues to be a central focus. The European Space Agency's upcoming JUICE mission to Jupiter's moons and NASA's Europa Clipper mission are set to explore these icy worlds in more detail, looking for clues about their potential habitability. One of the most exciting frontiers in astronomy is the study of the early universe. The discovery of the cosmic microwave background provided a snapshot of the universe when it was only 380,000 years old, but new observations are aiming to push our understanding even further back, to the first moments after the Big Bang. Upcoming observations from the James Webb Space Telescope, along with other instruments, will help astronomers probe the era of cosmic inflation, when the universe underwent rapid expansion. The greatest discoveries in astronomy have transformed not only our understanding of the cosmos, but also our view of humanity's place within it. From the realization that Earth is not the center of the universe to the discovery of distant exoplanets and the mysterious forces driving the expansion of the universe. Each new finding brings us closer to answering some of the most profound questions about the nature of existence. As we continue to explore the universe, new questions will arise, and new technologies will open doors to discoveries we can't even imagine today. Whether we're studying distant galaxies, probing the mysteries of black holes, or searching for signs of life beyond Earth, one thing is clear: our journey of discovery in astronomy is far from over. The cosmos is vast, and there is so much more to learn. Every observation, every experiment, and every theory brings us closer to unlocking the secrets of the universe. As we push the boundaries of human knowledge, we are reminded that astronomy is not just about understanding the stars. It's about understanding ourselves and our place in the grand tapestry of existence. The greatest discoveries in astronomy are a testament to the power of human curiosity and the relentless pursuit of knowledge. From the ancient astronomers who first mapped the stars to the modern scientists exploring the edges of space and time, each generation has contributed to a deeper understanding of the universe. And with each new discovery, we are reminded that there is always more to explore, more to learn, and more to wonder about. The universe is an ever-expanding frontier, and the greatest discoveries in astronomy will continue to inspire and challenge us for generations to come. Thank you for watching. Like the video? Be sure to hit the thumbs up and subscribe for more fascinating space discoveries.